Alright, so this is part 2 of the lecture covering chapter 22. Again, if you're not following along in the textbook, then this is just the next lecture. And the last one I left off telling you about some of the things we use to check our theories for the evolution of stars or how they evolve over their lifetimes. And at least the ones I told you about, the ones we're going to look at, are kinds of star clusters, stars together in a fairly confined area. So let's remind ourselves about that. So you have a bunch of stars that are all in the same kind of grouping, clustered. The two types we're going to look at or think about are these sort of open clusters and the globular clusters. The open ones are relatively young, dozen stars or so. Globular ones, very old, lots and lots of stars. The idea here is that since these stars are kind of all together, it's a fairly good guess that they've all been formed around the same time and from the same material. And so whenever we look at a cluster like this, we can sort of plot those on the HR diagram and check if the high mass stars are already on the main sequence that make it there first, or all the stars made it to the main sequence already. Maybe the high mass ones have started to leave already because they go through all their cycles quicker. Yeah, that's the general idea. A little bit more about the open clusters. Well, this one is an example. NGC 4755, also called the jewel box. It is about 6,400 light years away from us, and it's estimated to be about 14 million years old. 14 million years, a lot of years, but not so much when it comes to stars. And in just the image there, you can see the difference in color in the stars that make up this open cluster. A lot of them are more on the blue or white side, meaning they're hotter end of stars. At least one is really yellow. And apparently that one is a really massive star that's already made it to the main sequence and back off again and has become a giant. Generally speaking, for open clusters, they're relatively small. It's only a few dozen stars, or a dozen, few dozen, something like that. And the stars are not all that closely spaced. They're all sort of clumped together, but they're not necessarily that close together. And also overall, there's thousands of these kind of clusters in our galaxy. So a lot that we can look at. So again, in order to check our theories of how stars are born, and then later how they eventually move on to their sort of old age, right? We're going to look at these clusters and see how they plot on an HR diagram. So we can imagine, you have a bunch of stars that formed around the same time, so they're roughly the same age, and that means that they will all have started at like the far right, upper right end of these black lines, right? So we have a number of different stars, different masses, really high mass, lower, sun's mass, lower than that, right? And they start at these different areas on the HR diagram. And over time, they start to, they're still protostars and they're getting towards becoming a star. The more massive ones get to the main sequence a lot quicker. So by about 1,000 years, 10,000 years, that really, really massive star will have already made it to the main sequence. It'll be doing proton-proton fusion or hydrogen fusion. By that point, the 10 solar mass one is still fairly far away from the main sequence. The 1 solar mass one hardly will have moved much at all. So if you can imagine a really young star cluster we look at and plot it, only the most massive stars will have made it to the main sequence already, so you're going to have some dots along the main sequence, and the rest of them, as you get to lower and lower masses, will be sort of further away from the main sequence still. Something like this picture, where this is like a hypothetical cluster, so it's like a simulated cluster of stars, and they're only about 3 million years old. So at 3 million years old, the most massive stars have for sure already made it to the main sequence, right? They're already on that line, and even the ones not quite as massive, but still significantly more massive than the sun, have already all made it to the main sequence. They've gone through the full protostar stage, you've ignited their cores, and they're on the main sequence. Over here, though, you have this sort of arc of less massive stars that are still in their formative phases, right? They're still moving towards the main sequence. They haven't achieved that nuclear fusion yet. So if we look at a fairly young cluster of stars and we plot them on a diagram, like an HR diagram, where we go temperature versus luminosity, we would expect to see something like this. One such cluster is this one, NGC 2264, also known as the Christmas tree cluster, I guess. About 2,600 light years from us and about 30 light years across. It's estimated that this cluster is like 2 to 5 million years old. Right? So still pretty young. We would expect, if you plot all those stars on the HR diagram, you might get something like the expected one we just saw. So here you go. It's not perfect, but generally speaking, if you plot those stars in that cluster, then the ones that are in the higher mass are already on the main sequence. It's not quite as clean as being like right on this tiny little line or not. Right? There's still a decent amount of variation in stars that have made to the main sequence. Not necessarily going to be right on that line. But the larger stars, more luminous, are all pretty much on the main sequence, and then as you get lower and lower and lower, you start to get this arc of lower mass stars that haven't made it to the main sequence yet. So that was the prediction. That's sort of the reality for this star cluster, but it's a fairly easy portrayal of this whole process, and so there are a lot of other variables that can go into where a star is in its life cycle by this point. But overall, really massive ones on the main sequence, less massive ones still haven't made it to the main sequence. So a nice little check of our, at least simple understanding that more massive stars achieve nuclear fusion earlier, make it to the main sequence earlier, less massive stars takes longer. This is another plot, HR diagram, for an older cluster. This cluster is M41, and it's estimated to be about 190 million years old. So something like 100 times older than the Christmas tree cluster, and already has several red giants. So the redder dots in there are probably the red giants that they're mentioning. And so if we look at the stars plotted on the HR diagram, all the lower mass ones are on the main sequence. They made it to the main sequence a while ago. They're going to be there for a long time. And it's only then, once you get to the higher mass stars, those are the ones that will have gone through their time on the main sequence quicker and start moving off. And that moving off is because of the whole process I told you before, where the hydrogen fuel runs out, the core is left to just basically helium, mostly helium, and it's not fusing, so the whole gravity starts to collapse the star again, crushes the core, it heats it up. That reignites hydrogen fusion around the helium core, which heats up the atmosphere of the star, or the envelope of the star, and expands it. It expands and it cools. So it gets really big and it gets red. So it's thought that at least the stars on the far, or sort of the upper black dots, are more massive stars that are already moving into that red giant phase. And then there's some that are already way out here that are red giants. There's at least one dot on there that's a little bit confusing, one that's kind of hanging out by itself. Not really sure what to make of that, but again, this is glossing over a lot of details. So this is another hypothetical HR diagram. Maybe it's like simulating what we expect a plot of a bunch of stars to look like when they're about 4.24 billion years old, around the age of our star. Our star is 4.5, 4.6 billion, and it is for sure still on the main sequence. So in this hypothetical, our star is still one luminosity, about 5800 Kelvin. It'd still be in that region on the main sequence, but you go much beyond the size of our sun, maybe even to like twice the mass of our sun, most of those stars will start to move off the main sequence at this point. And the really massive ones are no longer even on this diagram anymore, because they have passed through their life cycle and have gone through their death throes, which talk more about that, or what those death throes are, in the next lecture or two. So the other kind of cluster I mentioned is this globular cluster, and there's an example of one there, 47 Tucanae, NGC 104. So as I mentioned, these globular clusters are generally very old. This one is estimated to be about 13 billion years old. which means it formed not that long after our universe began. Well, not that long, a billion years or so maybe. It's a bit further away from us than most of the other clusters that we looked at, or the younger clusters we looked at. It's 15,000 light years away. And that's partly because it's not actually in the disk of the Milky Way galaxy. Like I pointed out in the last bullet point here, there's about 150 of these globular clusters in our galaxy, but they tend to actually be more in what we call the halo of the galaxy. So the Milky Way, when you see, when you look out, is we're within the disk of the Milky Way, swirling around, and we're within it, so when we look out towards it, all we see is a sort of bar. So that's a lot of the mass that makes up the Milky Way, is that sort of spiraling disk, but the halo is sort of these areas above and below the disk, and it turns out that these globular clusters tend to be in our galaxy's halo, not in the disk. If you look at the image there, most of the stars that you see are yellow and red, maybe a little bit brownish. So these are the much cooler stars, and it's the cooler, lower mass stars that tend to take a lot longer to go through their life cycle. Some other general stuff about globular clusters is that they tend to be very old, rather symmetric, spherical, contain a whole lot of stars, and fairly large, 50 to like a few hundred light years across. So being very, very old, we would expect that if you were to plot the stars in this cluster on an HR diagram, there would be nothing in the high mass range, right? The really luminous stars. And so pretty much what you'd expect to be left is that the really low mass stars on the very far bottom right of the HR diagram, those are about the only ones still left on the main sequence. Everything else, even a star like our sun, will have probably left the main sequence by 13 billion years of life. So here you go. This is an HR diagram. As is noted here, this is like zoomed into an area of the HR diagram because earlier the left scale of luminosity went up to like 1,000 or 10,000 times the luminosity of our sun. So we're sort of shrinking in to only about 100 or so, 100, 200 times the luminosity of our sun. We're also zooming in on the temperature scale, right? Because before it went out to like 10 or 20 or 30,000 Kelvin. Now the only things that are left are, around 6,000 down to like 2 or 3,000 Kelvin. So same kind of diagram, temperature versus luminosity, but this is a much smaller portion of the diagram because there's nothing else left. All the other stuff up there has died quite a long time ago. These globular clusters are pretty nice for verifying predictions, at least over like the long time span of these lower mass stars. So this general sort of bar, or like diagonal, going down here, that's about where the main sequence is. So these stars, the lower half of this diagram, these ones are still on the main sequence. Even a star like our sun might be close-ish to still being on it. Now the rest of them up here have moved off the main sequence. They've finished their hydrogen burning phase and gone towards the red giant phase. You get well down here, things start to get a little weird too, so get a bit more spread out than just being on a lot. The overall sort of picture we get then from looking at clusters, remember again, look at clusters because all those stars are roughly the same age and then also made out of similar materials, formed at the same time, same place. So the only thing that differentiates them is how much mass really they started with. And so you look at these different clusters, we see this sort of pattern which conforms with our theories that stars only last on their main sequence for so long before they go off. And more specifically than that, the more massive a star is, the faster it's going to leave the main sequence. These plots then are even sort of more hypothetical, or just imagining that we have a bunch of stars and a bunch of different masses, and they all ignite their fusion core at the same time. If they do that at the same time, then they're all on the main sequence right at that same time. And so on the far left, these are all sort of like newborn stars that have all just been born in that instant. And what we predict and what we see happening when we look at these clusters is that the older these stars get, the lower this sort of turn-off point of the main sequence is. So after about 100 million years, all of the most massive stars that were way up in the top left have turned off the main sequence and have gone over to their red giant or supergiant phase. After about 10 billion years, that turn-off point will come all the way down here to almost near where our sun's turn-off point is. So when you plot these clusters, the sort of place where the stars have started to turn off the main sequence is indicating like how old that cluster is and how old those stars are in general. So that was a lot of information about sort of verifying or checking our theories for how stars evolve. Now we're going to start thinking again about what happens in the next phase of a star's life, right? Because where we ended off, we had looked at the birth of stars, and they start out in molecular clouds, and then these clumps form, and inside the clumps you have then cores that can form. Those cores can go to protostars to main sequence, and then after their main sequence time they can go to this red giant phase. After all that, a star will do one of a couple of things, and what exactly it does depends on how massive it is, and some other stuff. Again, glossing over a lot of things. There's also the wrinkle that the end life of a star can be quite different if it's part of a binary system or a triple star system or more. We're not going to worry about that here, so just focusing on like single star systems. I'm going to simplify the whole process even more by just kind of breaking the end life of stars, or this like really old age of stars after the initial red giant phase. It's going to break those into like two big categories, say like low mass stars and high mass stars. Very sort of oversimplified things, but this is a descriptive course, so that's what we're going to do. And that cutoff between high mass and low mass is about 8 times the mass of our sun. So stars that are less than 8 times the mass of our sun, we're going to consider low mass. Stars that are more than 8 times the mass of our sun, high mass. First, let's think about the low mass stars, right? Less than about 8 times the mass of our sun. So our sun would be included in these low mass stars. Okay? It's made it to its red giant phase, and so it's really large. The atmosphere is rather cool, so it's red, but there's that core of helium and that sort of shell of hydrogen around that core of helium, and the heat escaping from the helium core is causing fusion to happen in that shell of hydrogen. But during that whole time of the red giant phase, gravity is still crushing that core down, right, and heating it up, and heating it up, and heating it up. And eventually, those cores get hot enough where you are able to fuse helium. You start helium fusion. And for low mass stars, if stars like on the rather low mass size, like our sun or even less, then that first ignition of helium can happen very quickly, or a lot of the helium in the core can actually go, burn up really quick. So we call that a helium flash. In more massive stars, it tends to happen a little bit slower, so you don't get that flash event as much. But yeah, at that point, the core is hot enough to be fusing helium, and the process of fusing helium turns out to be what we call a triple alpha process. So alpha is a historical name for the nucleus of a helium atom. So the nucleus of a helium atom is 2 protons. 2 protons makes helium. The standard helium nucleus also has 2 neutrons. 2 protons, 2 neutrons. Helium nucleus, also called an alpha particle. This helium fusion process tends to go as a triple alpha process, meaning that 3 of these helium nuclei, 3 of these alpha particles, smash into each other at once, and then you end up with something that has 6 protons, 6 neutrons, it's carbon. This process of fusing helium then leads to a lot of carbon, right? That's sort of the next element that gets created. It turns out also that when you have that carbon around, it might get hit by another alpha particle, another helium nuclei, fuse to that, add 2 more protons, 2 more neutrons. That is then an oxygen nuclei. So in this stage where you're burning helium, you're tending to make a lot of carbon and then a little bit of oxygen, and I think even a little bit of neon. But eventually, that helium in the core is going to be exhausted, and what is left over then is that carbon that the star was then making from the helium, and also some oxygen. For these low mass stars, that's about as far as the fusion process is going to go. So they're not massive enough, they don't have enough gravitational energy to squeeze down the core enough to continue the fusion sort of chain, right? Because the next thing is, now that we've fused helium, what we got was basically a core of carbon and some oxygen, and this process could then maybe start over again if you could crush that core down enough to heat it up enough in order to start fusing carbon. For stars that are less than about 8 times the mass of the Sun, that's just not possible. There's not enough mass there. So towards the end of the fusion sort of chapters in a star's life, this is where you get. This is a low mass star, and still has hydrogen is the envelope. It makes up a lot of the very outer layer of the star. In that, there's a helium, and then finally inside of that is that carbon and oxygen that have been created by the fusion of helium. The other things that are going on here is that in some of these shells, like in one of the helium shells and one of the hydrogen shells, there actually is still fusion going on. And that's the same sort of process that gets the star to its first red giant phase. So if you recall, after a star was finished on the main sequence, it had this sort of core of helium and a shell of hydrogen outside, right? And the crushing down of that core generated a bunch of heat. It wasn't enough to fuse the helium, but it was still a lot of heat, and that heat transfers out and moves out through the hydrogen that's right around the core and heats that hydrogen up enough to initiate fusion in that shell. So in each step of this fusion sort of chain that's happening, where you're fusing heavier and heavier elements, the core needs to be hotter and hotter in order to get that fusion process going. And what that means is that it puts out a lot of heat into the outer shells. Even before it gets to a stage of fusion, enough heat to start fusion in those lighter elements that are now in sort of shells around the core. However, since these low mass stars won't really ever get hot enough to fuse carbon, the last sort of stage of this fusion is when that helium runs out in the actual core, and when it does, sort of like a car running out of gas, where it sort of sputters and sends out these like shock waves through the star. The result of that is that towards the end of that helium fusing stage, it ends up starting to like blow off the outer layers of itself. Right? So these outer layers of like the hydrogen and the helium, those sort of shock waves end up pushing off all these outer shells. And in the end, you're sort of left with that core of this low mass star, which will probably become what we call a white dwarf. But that's for the next chapter. This is part of like the death throes of the star. Something really cool that happens though with these low mass stars is those layers that were blown off during the last stages of its helium fusion, the last sort of time of its helium fusion, blowing out these layers. If the core that gets left there is still hot enough that it shines out a lot of energy and gives off a lot of light, particularly a lot of ultraviolet light, then that light can actually heat up the gas that it blew off, right? Those layers that were blown off of this star. And we get some of the coolest looking things in astronomy, which we call planetary nebula. I think I mentioned before, but planetary is a historical name, and it was given before it was understood what these things were. We're just still stuck with it. They're not planets. It doesn't have anything to do with planets. What it has to do with is the end, or very near the end, of a low mass star's life. So all these images are sort of the shells of stars that have been pushed off towards the end of its lifetime, and then they're being illuminated by some really intense light shining from the core that's left there. And the shapes of them can be rather different, some very irregularly shaped looking things. I think the bottom right one actually has probably gone through like multiple stages of blowing off its layers, and each of those stages looks a bit different when it's illuminated. There's a number of planetary nebulae that look like B there. You sort of these like tubes, and the core that's left is sort of in the middle, a white dot in the middle. Why it is that they end up in those shapes, the book talks about it a bit, but honestly I don't think we really know that well. I think it's probably fair to say that, you know, the rotation of the star will come into play. So just like in the very beginning of a star, or like pre-star, the rotation of all the material that was forming into the protostar made sort of this disk that blocked the equator, which meant that when the energy wanted to escape, it had to shoot out the poles. So there are reasons why you might get this sort of like eruption that seems preferential along the poles of a star. They're also just very pretty to look at. Rather short-lived sorts of things, and apparently they don't last for much more than a couple tens of thousands of years, which is very short on cosmic timescales. Being that they only last for such a short time, and we still see a good number of them, is a good indicator that they happen quite regularly. It's a fairly standard thing to happen for low-mass stars. As I mentioned a little bit, though, on the really low end of stars, they probably won't produce these planetary nebula because what's left over, that core, is just not really hot enough to illuminate this gas. And technically the illumination is ionizing the gas. We talked about the ionization process a bit. So usually when I say it's heating it to glow, it means it's ionizing that gas. It's actually not even really clear, I think at this point, if our sun is going to form something like this, or if it's just not massive enough to do that even. It's still going to blow off its layers at some point after its red giant phase, but whether some distant astronomer in the galaxy looking at our solar system can see something like this is kind of questionable. I'll just briefly mention this white dwarf, right? So what's left of the star after it blows off these outer layers? Well, you have the core that was left, and it's much denser than the star overall, and much smaller, much hotter. And as I mentioned, it's the radiation, the energy that's given off by these white dwarfs that's actually illuminating or causing the gas to glow in these planetary nebulae. It's another really cool one. This is NGC 6302, Butterfly Nebula, sometimes called. It's another one that looks like it sort of preferentially blew off its layers along its axis kind of fashion. We'll talk more about these a little later on. What about the high mass stars then? When the more massive stars get to their helium fusing stage, it tends to happen a bit more gradually. And then the big difference is that after it finishes fusing helium, the same sort of thing happens when it finished hydrogen. The core is not putting out energy anymore. It doesn't have that pressure to push back gravity, and so gravity takes over again and starts collapsing the core. And that happened in the low mass stars, but in the high mass stars, that collapse or that crush is enough to heat up the cores to start fusing the next element along, carbon. The exact process of the fusion, or like what things come together to make what, gets more and more confusing the further along you get in these stages. But basically we had carbon mostly left over from helium, carbon fuses, and we end up getting oxygen and neon, magnesium, and that makes up sort of the new core, and then the whole process sort of starts over again. The carbon runs out, it's not hot enough to fuse these larger things, and so gravity starts crushing the core again, right? And if it's enough mass, then it crushes the core enough to heat it up enough to start fusing the larger things. Right? So you start fusing neon and magnesium and such, and you make silicon, and also maybe sulfur, and then we go one more time, where that stuff sort of runs out. It needs to be much higher temperatures to fuse the silicon and sulfur, and so gravity has to collapse the star again, and each time you're sort of left with that ring of the stuff that was just fused, but is not close enough to the core the next time the nuclear fusion ignites in order to fuse itself. So what we get in these really massive stars are these very layered interiors. We'll see a picture of that in a second. But I want to mention now, once you get to the fusion of like silicon and sulfur, that is making iron. And iron turns out to be the most tightly bound nucleus there is, which means that if you try to fuse two iron nuclei together to make something bigger, it actually takes more energy to do it than you get out from the fusion process. So in all of these earlier processes, right, it takes energy in order to fuse hydrogen and hydrogen. It takes a lot of energy, and it takes even more to fuse helium. It takes even more to fuse carbon, right? But the output of that process, that fusing of the two protons when you're doing hydrogen fusion, there's more energy than it took to push them together, right? So in all these earlier processes, you're actually sort of net gaining the energy output, right? Which is good because that energy goes into increasing sort of the pressure of the star and balancing out gravity. Once you get to fusing iron, though, the iron starts to maybe want to start to try to fuse together, but it actually takes energy to do that. And so you net lose energy. The pressure overall starts to drop in the core. So once you get to that stage of having iron, and you try to fuse iron inside of the star, it's sort of a net loss. There's no gain in energy after that. And so iron ends up being like the sort of last stop of the core of stars as they're doing their process of fusing heavier and heavier elements. Iron is as heavy as it gets in the core. So here we have an HR diagram showing the sort of evolution of a star that's like our sun, 1 solar mass, and a star that's much higher mass, 15 times the mass of our sun, and evolutionary tracks as they finish out their sort of lifetime as a star doing nuclear fusion. The faded sort of line when it comes down and goes across over here, that's the main sequence line. And so our sun would be on main sequence there. After it finishes its hydrogen fusion, it starts to move off and do this other stuff where it gets maybe a little bit brighter but cooler, and then continues to get brighter and brighter and brighter and cooler and cooler. The really high mass stars then are already very bright, and it seems like they go through this little wiggle after they move off the main sequence where they're getting a bit cooler and brighter, and then they get a bit hotter and brighter, and then they start their helium fusion, and then they're just getting cooler and cooler and cooler. And again, the temperature we're looking at here is the temperature we measure of the star, right? So that's the outside of the star. So this high mass star stays relatively luminous, 10,000 times the luminosity of our sun, and its exterior just kind of gets cooler and cooler and cooler as it goes through the process of fusing helium, fusing carbon, fusing oxygen, and so forth. And there you go. That's the sort of picture we end up with for high mass stars. It's similar to low mass, just more layers, and we've managed to form heavier and heavier elements closer and closer to the core, where eventually the core ends up being mostly iron. I mentioned before that in order to begin fusion of these progressively heavier elements, the temperature needs to be higher and higher. So in order to fuse helium, we need a temperature of like 100 million Kelvin, whereas to fuse hydrogen, we only needed like 10 million Kelvin. And so it just keeps getting hotter and hotter and hotter. And another consequence of that is that the fusion process is going to go quicker and quicker and quicker for these heavier and heavier elements, right? Really, really high temperature, so the sort of burning rate goes faster and faster and faster. All the way up to the point where when you're burning silicon and you start to form iron, that phase, that silicon sort of fusion, or silicon and sulfur fusing phase, can be very quick. Right? According to the book here, once you start getting iron in the core, the star might only have a few minutes left before it's going to do something else, not be a star anymore. What that is, well, spoiler alert for next time, a high mass star, depending on how massive it is, might end up just blowing up entirely in what we call a supernova. But there are some more interesting things that happen besides that as well, and even during that process too. That's what the next lecture too is going to be all about, is the death of stars, low mass, high mass stars, how they go out. So I will see you later then.